Hello everyone. Today I am going to talk about CPU scheduling, a fundamental concept in operating system that determines how efficiently our computers run multiple tasks. Imagine you are in a queue at a bank or a grocery store. Some people arrive first, some have shorter talks, and some have higher priority like an emergency case. CPU scheduling works the same way. It decides which process gets CPU time, in what order, and for long time. Why is this important? Well, without scheduling, our system would be slow, or unresponsive, and unfair to users. Let's dive deeper. What is CPU scheduling? Every computer runs multiple tasks at once. Opening a web browser, playing music, running background updates, but there's only one CPU and it can execute only one process at the time per core. So the CPU scheduler steps in to manage multiple processes and ensure the system stays fast, fair and efficient. The main goals of CPU scheduling are minimizing CPU utilization, that is keep the CPU busy at all times, and then minimizing waiting time, reduce delays for process, and then ensuring fairness, that is no process should wait forever, and optimizing response time. Interactive program should respond quickly, and then improving throughput, more tasks completed in less time. Now let's look at the different types of scheduling in an operating system. Types of CPU scheduling. There are three levels of scheduling: long-term scheduling, short-term scheduling, and medium-term scheduling. First, speaking about long-term scheduling, decides which process enter the system for execution. Think of it like managing who gets into a crowded restaurant. Chooses which process gets CPU time next, like picking the next customer to be served. It is a short-term scheduling. And then medium-term scheduling is temporarily removes process from memory to optimize performance. It's like making a customer wait outside when there's no space inside. Each of these plays a role in keeping our system running smoothly. And let's speak about popular CPU scheduling algorithms. Now let's talk about different scheduling strategies, just like different ways of managing a queue. First come first served, shortest job next, priority scheduling, round robin, and then multi-level queue and multi-level feedback queue. Let's talk about first come first served. The simplest approach. A process are served in order they arrive. Problem: a slow process can block faster ones, causing conveyor effect like waiting behind a person with a hug order at a coffee shop. Next, shortest job next. The CPU selects the shortest job task first to minimize waiting time. Problem: longer task might starve because short tasks keep getting preference. And then third scheduling is priority scheduling. Each process has a priority and the highest priority task run first. Problem: low priority process might never run, and this is known as starvation. Solution of the priority scheduling is aging. Gradually increasing the priority of waiting process is called aging. And the fourth one is round robin. Every process gets a fixed time slice. This is quantum before switching to the next. Great for multiple multitasking because no process is left waiting too long. Downside: too many context switches can slow things down. And the last scheduling is multi-level queue and multi-level feedback queue. Divide process into multiple queues based on priority. Example: system task versus user applications. Feedback queue allows process to move behind queues to prevent starvation. Used in modern OS like Linux and Windows. And these are all the 5 CP scheduling algorithms. And let's talk about preemptive versus non-preemptive scheduling. There are two approaches of scheduling. Preemptive scheduling: the CPU can interrupt a running process to switch to another. Example: round robin and priority scheduling. Non-preemptive scheduling: once a process starts, it's run until it finishes. Example: first come first served and shortest job next. Preemptive scheduling ensures fairness. when non-preemptive scheduling reduces overhead. And then next, context switching, the hidden cost. Every time the CPU switches from one process to another, it needs to save current process state and load the new one. This is called context switching. Too much switching can slow down the system, like repeatedly switching between multiple tasks instead of focusing on one. How real world operating system handles scheduling. Let's see how popular operating system can handle CPU scheduling. Windows, Linux, Mac OS. Windows use a priority based scheduler with different priority levels. Linux uses the completely fair scheduler CFS for balanced performance, and then Mac OS uses multi-level feedback queue scheduling for efficiency. These strategies keep our device running smoothly. And challenges in CPU scheduling. Even with a great scheduling, there are some common problems like starvation, overhead, real-time scheduling. Speaking about starvation, low priority process may never run, and then overhead, too many context switches slow the system. And the real-time scheduling is nothing but system with strict deadlines, like medical device need special scheduler. And the future of CPU scheduling. As technology evolves, scheduling is getting smarter. Some future trends include AI driven scheduling, cloud based scheduling, and quantum computing. Speaking about AI driven scheduling, using machine learning to predict the best scheduling strategy. Cloud based scheduling, optimizing workloads across global quantum computing, new scheduling methods for quantum process. The future of CPU scheduling is faster, smarter, and more efficient. And the conclusion overall this is to sum up, CPU scheduling is crucial for modern computing. Different scheduling algorithms serve different needs, balancing fairness, efficiency, and speed. As technology advances, AI, cloud computing, and quantum processing will continue to refine how scheduling works, making our system faster and more efficient than ever before. Thank you for listening. I hope this gave you a clear and simple understanding of CPU scheduling in operating systems. Any questions? Leave in comments.